Ivan Korbenyenko, Marina Yashin, and Yaroslav Devianko.
Yes, I'm here and ready to make a report.
Thank you. Thank you. Please.
Can you see my presentation?
Yes, yes, please.
Okay. Hello, dear colleagues. I would like to thank the organizers of the conference for the opportunity to present our research. The topic of the report is method for obtaining DNA-based pseudorandom and random sequences using block encryption. In cryptography, random or pseudorandom sequences and numbers is required to construct various cryptographic primitives, keys, and system byte parameters. Our previous studies indicate the theoretical possibility of using DNA as a noise source and accordingly as a source of randomness. Our research consists of brief analysis of existing works in this area, proposals for a way to represent DNA in binary form for further use, and evaluation of the properties of such raw sequences, implementation of methods for obtaining DNA-based sequences with required properties by performing encryption using block symmetric chipper, a verification of the statistical properties of such yes.
Now changing, okay.
The efforts to improve the process of randomness generation are actively carried out at the international and national levels and require special attention. The importance of developing algorithm, method, and tools for generating computing random data is noted by the NIST and BSI. The point of the relevance of building new designs for obtaining randomness due to the need of improving cryptographic primitives that use random data and enhancing their security in order to resist existence and new attacks in the post-quantum period. The concept of using DNA in cryptography has already been considered in certain works. Paper 4 proposed the use of DNA as a key for encryption using the Robin cryptosystem and facial construction. The authors proposed a simple conversion of a DNA sequence into binary and use of such a binary sequence as a key. The described method of obtaining a key is questionable since the statistical properties of the raw DNA sequences do not fully meet modern requirements, as shown in our study. A similar example, which proposed to generate secure key using DNA-based one-time pad scheme, is given in 5. The shortcomings of described work is the need to use the key in OTP scheme only once, which is quite difficult to achieve using DNA. This is due to the fact that different parts of DNA sequences can be identical. Paper 6 uses a similar to 4 approach, but additionally provides the results of statistical tests of the data obtained. The results presented in paper are incomplete and the testing was performed on inappropriate data sizes, which questions the validity. In this article, we consider computational methods for obtaining pseudorandom and random sequences based on DNA. To obtain sequences with the required properties, we propose to perform encryption using the Ukrainian National Standard of Block Symmetric Encryption DESSERT'2024, Kalina. And to perform statistical properties testing, we use the International Standard of Statistical Testing NIS 822. The representation of DNA as a sequence of nitrogenous bases is shown on slide. The alphabet of DNA sequence contains of 4 possible values. Such sequences can be easily represented in binary form by replacing these values with unique binary combination that clearly shows the difference between these values. Since the alphabet consists of 4 values, to be able to represent these values in binary form, we need binary combination of lengths 2. DNA samples for further research were obtained from US National Library of Medicine and DNA Bank of Japan. In this article, we present the results of studies only for human DNA sequences, since the results obtained for other organisms are quite similar, which further indicates the possibility of considering DNA as a non-physical noise source. Using human DNA only is also justified by the practicality of its application. Since DNA is unique, sequences obtained from it can be used as unique data. Thus, after obtaining a sample of one sold DNA, a person can use it to obtain, for example, unique secret keys. As can be seen from the result of testing, the statistical characteristics of the raw sequences are not satisfactory. Almost all statistical tests defined in NIST 822 are failed. This may indicate a significant deviation from uniformity. The results of the entropy testing method indicate the presence of certain amount of entropy in such sequences. This shows the theoretical possibility of conditioning such sequences using, for example, a block chipper with required level of security, as recommended in NIST 890A and C. To obtain the sequences in this paper, we use an extractor based on the Ukrainian national standard of block symmetric encryption. The use of such crypto primitives for sequence conditioning is justified in IEEE 2031 and NIST 890B. Steps to generate pseudorandom sequences are shown on slide 9. To generate pseudorandom sequences, key and nonce obtaining by hashing internal state of the generator with particular value. Steps to generate sequences, random sequences are shown on slide 10. To generate random sequences, key and nonce obtaining as a random string by true random number generator. Thus, the standard allows the generation of pseudorandom and random sequences depending on the input parameter. To analyze the properties of the resulting pseudorandom and random sequences, we generated 6 sequences of length 13 megabytes and 6 sequences of large length 144 megabytes. To independently verify the results obtained in this work, it is necessary to get a DNA sample from one of the mentioned databases represented in binary form and use one of the presented generation algorithm with appropriate block chipper. The results of the analysis show that the output of the standard has good statistical values. For the 96 criteria, almost all of 189 tests for each sequences were passed, which means that there are no statistical significant defects in them. Statistical portraits of such sequences are shown on slide 11. The results of the statistical analysis of random sequences also indicate that the statistical testing was successful. They show almost the same test pass rate as the pseudo-random sequences, which also indicates their uniformity and the absence of statistical flaws. Portrait can be seen on slide 20. The results obtained indicate that the output of presented generator meets the requirements of the NIST 822 recommendation. The failure of some sequences of one test from the set can be considered a statistical anomaly, since the results for other sequences, including those of larger sizes, which give a more accurate estimate, indicate the complete success of the testing. It should also be noted that NIST suggests an approximate limit for passing. The obtained result can have practical application in construction where randomness is required, in computing of keys and system-wide parameters, in performing transformation as part of hash function, in obtaining sequences of an arbitrary alphabet, in zero-knowledge protocol, etc. The results can also be used in areas outside of information security. Previous studies have shown the possibility of obtaining binary data based on DNA, but such data has not quite satisfactory properties. The results of testing using entropy method show the presence of certain amount of entropy. This indicates the possibility of applying conditional component to such sequences, using, for example, block chipper. The presented in article method allowed to quickly compute DNA-based pseudo-random and random sequences using a national standard. The analysis of the statistical properties of the sequences obtained in this way shows their statistical indistinguishability, and therefore these sequences can be used in necessary tasks. The issues of providing other characteristics of generator based on Ukrainian national standards, such as forward and backwards accuracy and improved forward and backwards accuracy, remains open. This will be investigated in future works. Thank you for attention. Please ask the question.
Thank you very much for your lecture. Have we please any questions?
I have some question.
Yes, please, Professor Markovsky. Please.
Tell me, please. We know that the standard provides for linear complexity assessment, and I interest in have you performed a linear complexity defined for your generator sequences? Can you take us the estimated of linear complexity, because we need estimate the linear complexity.
No, we just not yet perform the
But
estimate.
you know that this estimated is in NIST, So every pseudorandom binary sequences must be defined according to the standard the linear and non-linear complexity. Because of we must estimate the complexity of reproduction model. This is my first question. Another question is very important. Can you comparing your generating method to some standard method, for example, I5? I think that standard method are more effectively because of very quickly in comparing to your method.
Mm.
What can you say about it?
We just not yet compare this method with other method.
But R5 is standard method, is existing method in all country now for military application, for example.
Not only for military, for every method. So yes.
Thank you. I have not any question.
Yes. It's very interesting new work obtaining DNAs with pseudorandom and random sequences, and of course, yes, for future work, it's you have to make a lot of work with your research team. Yes. Have we any more questions, please? Thank you. So considering your future works, or if you have time until the camera ready, to update your paper with the comments of our also co-chair, Professor Makowski, and we will be glad to with the reviews to see, etc. This work. Okay, thank you very much.
Thank you for your
Thank you
question.
very much. Thank you very much. So